Here's your next video for Chapter 1, and we're going to get into the nitty-gritties of significant figures. Now, in the previous video, at least toward the end there, I made reference to sig figs, significant digits or significant figures. And now we're going to talk about what they're for, why do we use them, why do we care. So significant digits give us an idea of how good a particular measurement is. Okay? In other words, how precise is that measurement? So as an example, so let's say I've got for some reason I want to take a measurement of the length of a rock. Okay, I think actually in my handwritten notes it's like kind of looks like a quarter or a circle with a badly drawn bird on it, and I decided not to try and recreate the bird. That aside, so let's say we want to take a measurement of this rock, and I've got a ruler that only has 1-inch marks on it. Okay, so we take a look at this, at where this lies, and let's say that it sits right about there. Okay, so based on the ruler that I have, I'm certain of at least 1 inch. All right, I know for sure that it's something past 1 inch. So the 1 I'm positive about. And then I estimate the next digit. All right, so measurements to the correct number of significant figures contain the certain digits and then always end with one estimated digit. So if I were to say estimate where that sits, I'm going to say that it's somewhere around 0.4. So if I were to, using this ruler, if I were to say what is that measurement, I can say the best I can say is 1.4 inches. Right, so thinking about what those numbers mean, that's my certain digit, and that's my estimate. Or we can say uncertain digit. Right, so all measurements to the correct sig figs have one uncertain digit at the end. Right, so given what I have here with this ruler, I'm not likely to be able to, with any certainty, say 1.46, because I can't estimate farther than the 4. Makes no sense, right? But let's say we did have, say, a half mark and the rest of our marks. Right? Now that I have more precision in my measuring tool, I can add another digit on there. Now I'm positive of 1.4, and I can estimate one more digit. So I could say 1.42, for example. So the more digits you have, the more certain the measurement is, and the more precise the measurement is. More certainty. Okay, so the more precise your measuring tool, the more digits you get and the more certain you are of your measurement. Okay, and this is going to be something that we'll get into a little bit more with lab. But proceeding forward from here on out, the number of significant digits will always count. It will always matter to whatever calculation we're doing. So when you're looking at a number, how do you determine how many significant figures there are? And I shorten it to sig figs. A, it's easier to say, and B, it's easier to write. Okay, so but it stands for significant figures. So there are rules to determining significant figures of a number. So the first rule is that all non-zeros are significant. Okay, the second rule is that zeros between non-zeros are significant. The third rule is that all trailing zeros are significant, with one caveat, with a decimal place. And the fourth rule is all leading zeros are never significant. All right, so let's talk about that caveat of trailing zeros with the decimal. So if I have number 75000 with no decimal place anywhere, this number might have, so all non-zeros are significant, so the 7 and the 5. Trailing zeros are significant with a decimal. So that means that these digits are ambiguous. Okay, so, but if I put a decimal place there, now they count. Okay, so one way to avoid this is scientific notation. Helps to avoid ambiguity. All right, so an easier way for me to write this 75,000 and tell exactly how many significant digits there are would be for me to say 7.5 times 10 to the 4. So let's go ahead and do a little bit of practice with identifying the correct number of significant digits in a value. So we've got, for example, 7500.1. So all non-zeros count, and all zeros in between non-zeros count. So this number has 5 sig figs. Right. 7500.10. Right, all non-zeros count, all zeros between non-zeros count, and all trailing zeros count. In other words, this 0 to the right count as long as we have a decimal place. So this number has 6 sig figs. Right. 0.0075. Non-zeros count. Zeros to the left, the leading zeros, never count. Okay, so these zeros to the left never count for significant digits. It only tells us where to put this decimal place. So this number only has 2 sig figs. If I have 0.00750, the leading zeros don't count, but the trailing zeros do. So this number has 3 sig figs. Right now I'm thinking about scientific notation. How do we do sig figs for scientific notation? 9.41 times 10 to the 17. When we're trying to decide sig figs for scientific notation, we only look at the coefficient. And in this case, it's all non-zeros, so this number has 3 sig figs. All right, we ignore the times 10 to the 7. All that is a multiplier. It doesn't actually have anything to do with our number. 1.9741 times 10 to the minus 5. Again, we only look at the coefficient, so this number has 5 sig figs. All right, so exceptions to the sig fig rule. Okay, so earlier we talked about how if a number has more digits, that means that it is more certain. Okay, we are more sure of that number. So the more digits, the more certain we are. Well, so what happens when we are infinitely sure? Okay, so that's where we run into exceptions to sig figs. Right, so exceptions fall under two categories: definitions. Okay, so things like 1 minute equals 60 seconds. Right, that's a definition. 1 inch is exactly 2.54 centimeters. That's a definition. 1 ton equals 2,000 pounds. Okay, so 1 millimeter is 10 to the minus 3 meters. These are all definitions. And definitions are said to have an infinite number of significant digits. Okay, the other thing that falls into that category are counting numbers. Right, so things like 6 faces to a cube, or to be more sort of chemistry oriented, 2 hydrogens per water molecule. Right? You can think about counting the number of people in a room or cars on the street. For example, you're not going to say that there's 4.6 human beings in the room. You're going to say that there are either 4 human beings or 5 human beings. You are infinitely sure of the number of things there. Okay, so if you have 7 pennies in your hand, it's not 7.1 or 6.9 pennies. There are exactly 7 pennies. Right? So counting numbers and definitions, we say they have infinite significant digits. Because the more digits, the more sure we are. So if we have infinite significant digits, that means that we are infinitely sure of that number. Okay? So I'm going to go ahead and stop this video right here, and we'll come back with the next video and talk about doing calculations with significant digits.